Hello, this is a video lecture aimed at presenting the TOCTOU problem that is encountered during remote attestation in the context of IoT devices. The contents of this video presentation are based on the research paper titled in the screen and whose authors are Ivan Oliveira, Shashidhar Jakamseti, Norathep Ratanavipanan, and Jean Sudik. Throughout the course of this video, we will address the following issues. Firstly, the current landscape of the Internet of Things, the devices it utilizes, and what complexity of operations are these devices expected to perform. We will also look at the current standard for such devices in the industry, as well as some examples. Then we shall look at remote attestation, its definition, and why is it such a crucial part of IoT systems. Followed by the TOCTOU problem, specifically what is about RA that causes this to be a security vulnerability, and what limitation does an RA face while trying to mitigate this vulnerability. We will then discuss about a potential solution to the TOCTOU problem, RATA, a TOCTOU secure technique for ensuring device memory is not corrupted. We will then evaluate these solutions against traditional RA architectures and compare the results mathematically. Finally, we will conclude our results and discuss further improvements to the RATA architecture. Over the last couple of decades, the sheer number of smart devices has increased dramatically. These devices have different kinds of specialized functions and are often called smart devices or IoT devices. They have diverse applications in our daily lives, but at the same time, because of their relatively simple design, they have become a lucrative target for bad actors. An example of a very specific type of IoT device would be a microcontroller. This device, residing at the low end of the IoT spectrum, is designed with strict monetary, physical, and energy consumption constraints. These microcontrollers, although on the low end, are very similar in their functionality to some of their higher end counterparts. Two prominent microcontrollers are MSP430 by Texan Instruments and Atmel Atmega AVR. However, as we saw in the previous slide, there are many limitations to the physical capabilities of microcontrollers. They have limited memory, limited storage, and therefore no practical means to implement security measures. As a result of this, it is inefficient to expect these devices to perform software integrity checks every time when they boot up. Therefore, to prevent these devices from getting exploited and to implement good security, remote attestation was defined as a security procedure for these devices. Remote attestation is a cheap yet extremely effective method of detecting unauthorized modification to executables of remote low-end devices. Remote attestation is also responsible for maintaining other important security services in these devices, such as software updates, control flow integrity verification, and proof of remote software execution. We shall now look at the working of the remote attestation protocol. In the RA landscape, the RA module allows a trusted entity called a verifier, denoted here with VRF, to understand the memory integrity of an untrusted remote device called a prover, denoted here with a PRV. In this scenario, RA is realized as a challenge response protocol. In the first step, VRF sends an attestation request with a challenge called CHAL to PRV. The provider, when receiving this challenge, requests and computes a challenge-based authenticated integrity check over a memory region. This check could be a practical function like HMAC. After computing this result, the prover then returns this result to the verifier. The verifier, after receiving this result, checks whether it corresponds to a valid memory state. We shall now attempt to formalize the challenge response protocol that was mentioned in the previous slide as the syntax which you can now see on the screen. The first function in this syntax is request. This is the algorithm that will be initiated by the verifier to request a portion of the prover's memory's attested range. As part of the request, the verifier will send the challenge to the prover as well. The second function in this protocol will be attest. This is the algorithm that will be executed by the prover upon receiving the challenge from the verifier. This algorithm calculates an authenticated integrity ensuring function like HMAC over the attested range content. As a result of this calculation, it will produce the authentication token H, which will then be returned to the verifier. Finally, the last function in this protocol is verify. This algorithm is executed by the verifier upon receiving the authentication token from the prover. This token verifies whether the current content in the prover's range corresponds to an expected value M. The verification mentioned in the last slide is only made possible in computer systems by following three steps. Firstly, identifying the system of interest using a formal model such as an FSM or a finite state machine. Then, the properties that this model should satisfy are formally specified. Finally, this model is then checked against the formally specified properties to guarantee that it retains them. In one method of checking, the properties can be specified as formulae, wherein the system's state would be represented by a tuple S, S0 and T, where S is the finite set of states, S0 is a subset of S and is the set of all possible initial states, and T is a transition relationship set defined by the relationship S cross S0. Despite all the advances that have been made in the current state of RA architecture, they all have one fatal flaw. They measure the state of the prover executables at the time when RA is executed by the prover. They provide no information about prover executable state before RA is measured or of its state between two consecutive RA measurements. Where this becomes a problem is with transient malware. Transient malware has the capability of deleting itself after carrying out its nefarious actions. This would mean that the state of the controller would be reported normal even though it has been corrupted by the malware. And even though the state is not the correct value, there is no way to check this since there are no intermittent RA measurements. This problem in controller systems is known as the time of check and time of use, or the TOCTOU problem. Before we formally attempt to write down a definition for RA, let us look at some notation we will be using. Although most RA techniques are not associated to any architecture, for all practical purposes pertaining to this video, we shall be using the V raised formal security definitions. Most of the notation used here is consistent with V raised 10, with a few additional elements to denote RATA specific elements. In addition to notations, we would require some axioms to formalize our RA TOCTOU notation. Number 1. Program counter. The program counter always contains the address of the instruction being executed in any given CPU cycle. Number 2. Memory address. Whenever memory is read or written, a data address signal contains the address of the corresponding memory location. For a read access, data read enable bit must be set. For write access, the data write enable bit must be set. Number 3. DMA. Whenever the direct memory access controller attempts to access the main system memory, a DMA address signal reflects the address of the memory location being accessed, and the DMA enable bit is set. DMA cannot access memory without setting DMA enable. Number 4. MCU reset. At the end of a successful reset routine, all registers, including the program counter, are set to 0 before resuming normal software execution flow. Resets are handled by the MCU in hardware. Thus, the reset handling routine cannot be modified. When a reset happens, the corresponding reset signal is set. The same signal is also set when MCU initializes for the first time. And finally, number 5, no data execution. This means that instructions must reside physically inside program memory in order to execute. They are not loaded to data memory to execute. In conformance with the axioms discussed on the previous slide, we can use these axioms to denote a modification to memory address X. Given our machine model, these formulae capture the fact that a memory modification can be caused by either the CPU or by the DMA. We can use this notation to represent a modification to a location with a contiguous memory region R as equation number 4. This definition captures the notion of TOCTOU security. The game formalized the threat model where the adversary controls the prover's entire software state, including the ability to invoke a test function at will. The game starts with the challenger choosing a time t0. At a later attack timing, the adversary receives the challenge and wins the game if it can produce the secret token that is accepted by the verifier as a valid response for expected attested range value M. This definition augments security by allowing the adversary to succeed if it produces the expected response even though the attested range was modified. Therefore, TOCTOU security in this manner can be defined by the security parameter L that has to be optimized in such a way that with the probability of L being negligible, the probability of adversary successfully guessing the token and winning the TOCTOU security. This definition captures the notion of TOCTOU security. The game formalizes a threat model where the adversary controls the prover's entire software state, including the ability to invoke the attest function at will. The game starts with the challenger choosing a time t0. At a later attack timing, the adversary receives the challenge and wins the game if it can produce H that is accepted by the verifier as a valid response for expected attested range value M. This definition augments security by allowing the adversary to win if it succeeds in producing the expected response, even though the AR was modified. Therefore, security against TOCTOU in this manner can be defined as a parameter L that can be optimized in such a way that the probability of the adversary winning this game is negligible. RA schemes based on self-measurement attempt to detect transient malware by intermittently and unilaterally invoking the RA function. It then self-reports to the verifier or stores these values locally. Upon receiving these measurements, the VRF checks for the presence of malware. Clearly, all self-measurement schemes have to leave some time between consecutive RA checks. To shorten the duration, the CPU would have to invoke the RA function many times within a given CPU cycle to leave no gap for transient malware. This would mean that a large fraction of CPU cycles would be spent on RA computation. Therefore, detection of transient malware using self-measurement is not only inconvenient but also highly impractical. We now overview RATA-A, a simple technique that requires the prover to have a reliable read-only real-time clock synchronized with the verifier. However, real-time clocks are not readily available on low-end MCUs, and secure clock synchronization in distributed systems is challenging, especially for low-end devices like the MSP430. Nevertheless, we start with this simple approach to show the main idea behind TOCTOU Secure RA. RATA is illustrated and designed as a verified hardware module that behaves as follows. It monitors a set of CPU signals and detects whenever any location within the attested range is written. This is achieved by checking the value of the signal's data address, write enable, direct memory access address, and direct memory access enable. These signals allow detection of memory modifications either by the CPU or by the direct memory access controller. Whenever a modification in the attested range is detected, RATA-A logs the timestamp by reading the current time from the real-time clock and storing it in a fixed memory location called the latest modification time, or the LMT. In the memory layout, the LMT lies within the attested range. Also, RATA A enforces that LMT is always read-only for all software executing on the MCU and for the direct memory access controller. Note that by enforcing the rule that the least modification time lies within the attested range, the attestation result H includes the authenticated value of the least modification time as well. This will be the time corresponding to the latest modification of the attested range. Construction 1 on the previous page assumes that properties in equations 11 and 12 are enforced by RATA A. This figure shows a formally verified finite state machine corresponding to this implementation. It enforces two properties of equation 11 and 12. This finite state machine is implemented as a Mealy machine, where output changes any time based on both the current state and the current input values. The state machine takes as an input a subset of signals and produces two 1-bit outputs: reset to trigger an immediate reset, and set LMT to control the value of LMT memory location. Reset is 1 whenever the state machine transitions to reset state, and while it remains in that state, it remains 0 otherwise. Whereas set LMT is 1 when the state machine transitions to the mod state and becomes 0 whenever it transitions out of the mod state. For all other cases, LMT is set to 0. The state machine works by monitoring write access to LMT and transitioning to reset whenever such attempts happen. When the system is running, the state machine also monitors write access to the attested range and transitions to the mod state whenever that happens. The state machine transitions back to the not mod state if the attested range is not being modified. We now describe RATA B, a TOCTOU secure technique that requires no clock on the prover. We apply the ideas from RATA A by using hardware to convey authenticated information about the time of the latest memory modification as part of the attestation result. However, the lack of a real-time clock prevents any notion of time on the prover. To cope with this, we rely on the verifier to convey information tied to a given point in time, according to the verifier's own local clock. This is done as part of the RA request algorithm. In fact, RATA B uses the attestation challenge itself for this task, taking advantage of the fact that the challenge is unique per request and is available in any RA technique, thus incurring no additional communication overhead. Security of RATA B is tightly coupled with the authentication of the verifier request, which is already part of the V-raised architecture. The design of RATA B remains consistent with that of RATA A. RATA B monitors the same set of MCU signals as RATA A and also works by overwriting the special memory region LMT, or last modified time, which belongs to the attested range. However, instead of logging an real-time clock stamp to the last modified time, it logs challenge, which was sent by the verifier as part of its request and given as input to the attestation challenge. The last modified time is overwritten with the currently received challenge if and only if a modification of the attested range occurred since the previous attest instance. In short, RATA B security relies on the following properties enforced by its verified hardware implementation. Similar to RATA A, no software running on the prover can overwrite the last modified time. That is, the last modified time is only modifiable by RATA B hardware. Also, an update to the last modified time is triggered only immediately after successful authentication during a test computation. And finally, the first successful authentication happening after a modification always causes the last modified time to be updated with the current value of the challenge, which is stored in MR, which is the memory location that the attest function reads from the value of challenge. The figure shown on this slide shows a RATA B implementation as a finite state machine formally verified to adhere to the properties mentioned on the previous page. It takes an input as a subset of signals and outputs two 1-bit signals, Reset triggers an immediate system-wide reset, and up LMT controls updates to the LMT region. Up LMT equals 1 whenever the finite state machine transitions to state update and has value 0 in all other states. Reset is set to 1 whenever the finite state machine transitions to the reset state and remains unchanged while it is in the state. Otherwise, it remains 0. The finite state machine operates as follows. If a software modification of the last modified time is attempted, the finite state machine triggers reset immediately, regardless of what state it is in. If no modifications are made to the attested range, since the previous computation of attest, the finite state machine remains in not mod state. At any point in time, if a modification to the attested range is detected, the finite state machine transitions to state mod. This transition indicates that a modification occurred, although it neither alters any output nor modifies the last modified time. This is because the information to be written to the last modified time is not available at this time. When a call to attest is made, two possible actions can occur. If the finite state machine is in not mod state, a test is computed normally and the finite state machine remains in the same state. Otherwise, the state machine stays in the mod state until the condition program counter is equal to the CR auth is met, implying successful authentication of the verifier. Then the state machine transitions to state update, causing up limit to be set during the transition. Hence, the last modified time is overwritten with challenge passed as a parameter to the current attest call. Note that update to the last modified time happens before the computation of the integrity ensuring function HMAC over the attested region, which happens in the state attest. On this slide, we discuss the overheads the RATA implementations require. Runtime overhead. RATA does not require any runtime overhead. Memory overhead. RATA A requires 128 bits of additional storage, whereas RATA B requires an additional memory overhead of 512 bits. Verification resources require less than a second and consume at most 26 MB of memory. Finally, when comparing both our RATA implementations to SEED and Erasmus, which are recent self-measurement RA techniques, both use less LUTs than self-measurement techniques, and both RATAs incur low overhead for both LUTs and registers. Finally, we shall look at some RA enhancements using RATA. Number 1, constant time RA. The most notable and beneficial feature of RATA is that most of the time, RA no longer needs to be computed over the entire attested range, which significantly reduces RA execution time on the prover. Secondly, atomicity. Security of hybrid RA architectures generally depends on temporal consistency of attested memory. Simply put, temporal consistency means that the attested range was modified during RA computation, the lack of which allows transient malware to move itself within the prover memory during attestation in order to avoid detection. If malware interrupts attestation execution and relocates itself to part of the attestation range that has already been covered by the integrity ensuring HMAC and restarts attestation, this will cause the malware to dodge. Secondly, collective RA. Collective RA protocols, aka swarm attestations, are a set of techniques that attest a large number of devices that operate together as part of a larger system. CRA schemes typically assume hybrid RA architectures on individual devices and look into how to attest many devices efficiently. One security problem that is typically out of scope on single device RA and becomes relevant in CRA settings is caused by migratory malware. This is analogous of intra-device self-relocating transient malware that appears in collective settings. Specifically, instead of moving around inside the memory of the same device, it migrates from device to device, avoiding detection. And finally, runtime attestation. Runtime attestation focuses on detection of runtime or data memory attacks, providing authenticated information about software execution on the prover. While it seems unrelated to detection of retrospective program memory modifications, RATA can offer improvements to runtime attestation techniques.